Namaskar and welcome to episode number 2 of Understanding Feynman's Physics. Yesterday we introduced ourselves to the new way of thinking about electromagnetism, where we said that it's not the best way to think of electromagnetism in terms of forces between charges. Okay, that's what we do with gravity, right? When we try to figure out forces between two objects gravitationally. That's one way to look at gravity. That's the main way to look at gravity, right? We realize when we look at electromagnetism like that, and when we put the laws of electromagnetism in those terms, in terms of forces between different charges, it is a much more complex way of looking at the effects of electromagnetism, as it turns out. That's what Richard Feynman says. I went back and looked at the equations, and it's really not the prettiest equations. They are complex. And this is what Feynman says in the book. He says, it turns out that the form in which the laws of electrodynamics are simplest are not what you might expect. It is not simplest to give a formula for the force that one charge produces on another. It is true that when charges are standing still in Coulomb's force law is simple, but the problem is when the charges are moving. That's when the problem comes. If the charges are stable, you can easily figure out the forces between them, right? But when the charges are moving, the problem is of the magnetic field, and that creates a lot of complications, because magnetic field is a result of change in electric flux. We'll figure it out. We'll see. Okay. So yesterday we said there is this number at every point in space, which number is the electric field and the magnetic field, the power of these fields. There is a specific number and a direction of the possible force that will be applied to a charge that is present in that place, in that position, right? The point is, if you remove that, since just consider, let's restart. Just consider like a huge universe of a lot of particles, right? And each particle might be moving around randomly and creating electric and magnetic fields, and all those electric and magnetic fields have an effect on the whole of the universe, the whole space of the universe, right? At every space, at every point in the universe, there will be a value of the resulting electric and magnetic field that we can figure out from this. This is the thing that we used yesterday to calculate the force, right? Now, what is the idea is that just if you remove any charge, just that electric and magnetic force, the field that is remaining, what we can do is we can map it. It's easy to it's possible to kind of show it visually in terms of these vector lines going across. This is one way. There is one way to do it. At every point on the paper, the direction of the arrow is proportional to the size or the magnitude of the field. How strong is the field in that at that point, and the location of the point is, of course, where we are talking about what we are talking about, and the direction and the length. The direction of the arrow is the direction of the field, and the length of the arrow is the magnitude of the field, right? That's one way to see it. He says the best way, the most correct way to think of it is the simplest. Is also the most abstract. where we just simply consider the field as mathematical function of position and time, right? Just at every point we think of that there is a field, the direction of the possible force on our pet charge, our charge that we put there, and how it changes as we move the charge from one place to another, and how it changes when we move the time, when we go into the next second, right? That's the most abstract way of thinking about it. There is a third way of thinking about it. I think this is what I remember from childhood, where we have these lines that are going through, and they're like curvy lines. You might have seen them in magnetic diagrams. When there is a magnet with the North Pole and the South Pole, lines start from the North Pole and go into the South Pole, right? Or the other way around. Is it the same? Depends on how you are thinking of the arrows. The direction of the arrows doesn't matter. But the point is that at every point, this curve um, tangents the direction of the field at that point, and the intensity of the field can be understood to be proportional to the density of these lines. If the lines are too dense, close together, the field is stronger. If they're far apart, the field is weaker. Okay, so if you don't understand much, it's fine. But the point is, this is a way to understand these lines, right? Now, how does that help us? Well, there are two things we'll discuss today. Two ways of looking at it, and then that's it. A small dose of complex physics. Don't worry. Do not be alarmed. This is one way to look at it. You take a closed surface, right? You take a closed surface like a ball. Okay, it's a big volume. It's a closed surface. An open surface is like a paper. A piece of paper is an open surface. A closed surface is like a ball. Okay. The flux is defined. You define something called a flux. Flux is defined as the tangential component of the fields that are coming out of that surface times the area of that surface. So let's say a paper is on top of a charge. Okay, there's a charge at the center, and there is a piece of paper lying 1 meter away from it, right? So there'll be electric field coming from the charge towards the paper, right? So the flux through the paper would be the normal component, the component that is perpendicular to the paper. At the center, let's say the center of the paper is aligned to the center of the aligned to the charge, such that most of the all of the electric field hitting at the center goes directly through, right? So we'll have sort of a tangentially reducing strength as we go outwards from the center of the paper, and we just take the normal component and multiply it by the surface area. That's the flux. Basically, it's the amount of electric field going through that surface, right? Now he says there is a second component called the circulation. We looked at the tangential component. Sorry, we looked at the perpendicular component. What about the other tangential component, right? The tangential component, and we only define it through an arc, or through a curve, not through a surface, just a curve. and that is basically the tangential component on each. Let's say it's like a flowing river, and a turbulent river flowing in all over the direction. It's hitting the stones, and water is traveling all over the place. What you do is you put a tube, an imaginary tube, in the water, which is a closed loop, and you think of it as this is what he writes. Think as you suddenly flash freeze all of the water on the outside of the tube, but on the inside, the water is still allowed to flow just in that tube, right? The rest of the water, the outside, will freeze without any change in anything. Just think of it as just frozen. There will be still some momentum in the water that is flowing in that circular loop, right? Only that part of the velocity that is tangential, that is going through the loop rather than away from, rather than tangential, perpendicularly out of the loop, will be a part of this circulation. And circulation is basically the average tangential component multiplied by the distance around the circumference of that tube. Okay, that's circulation, right? Now he says, Feynman says that the laws of electromagnetism can be defined in these terms very simply. We'll just state them today, and then tomorrow we'll explore them more. He says that if you think of a ball, a surface of a ball, right? If there is no charge inside the ball, the flux going into the ball should be the same as flux going out of the ball, and the flux of B, flux of this flux of E through any closed surface, whatever is coming in is going down. The net is zero if there is no charge inside that ball. That's one law. All right. Right? That's proportional. If there is a charge inside that ball, the flux would be positive, because more lines are coming out of the ball than are going into the ball, because there is a charge inside. If the charge is stationary, we can understand that Coulomb's law is exactly that. How? Let's say there is a charge at the center, and then there is an imaginary ball 1 meter with 1 meter radius, right? The flux is the intensity of the field times the surface area. Okay, surface area is proportional to square of radius, right? As we increase the size from 1 meter radius to 2 meter radius of the ball, the surface area increases by 4 times, but the flux should be proportional to the charge inside. So it must not change. It should be the same for the smaller ball and the bigger ball, right? But if the surface area has increased by 4 times, and flux is surface area times the normal component of the field, the perpendicular component of the field, the perpendicular component of the field should reduce by 4 times, so that the flux remains the same. The flux remains the same because it's proportional to the charge inside the ball. If the radius of the ball increases by 2 times, the surface area of the ball increases by 4 times, and then the strength of the field should reduce by 4 times, which is the inverse square law. That is the inverse square law. And we'll stop here. There are 3 other laws that come out of it. And Feynman says that this is the best way to show it. All of the electromagnetism can be understood by these flux and the circulation of these fields. And we'll see more. It's a little too complex. It's a little complex. I understand. I agree with you guys. If those of you who are thinking it's complex, those of you who are thinking it's easy, I do not agree with you. I'm sorry. Apologies. This thing is a little complex, but I think it will give us some understanding of how physics is and how it works. I was good at physics when I was in college. No, not in college, in school. In my high school, 11th, 12th. I was good. I was not bad. I was good. But now I have forgotten most of it. I've forgotten the thrill. No, I haven't forgotten the thrill. I'm sorry. Apologies. I love it. I love the fact that there are so many. I can see it from these adult eyes now. All these things, even though I am not as sharp as I used to be when I was in school, because I was learning all the time. Now I'm not learning these complex things in mathematics and physics. But I hope as we go along these episodes, I will get sharper and maybe even more well be able to explain things to you. In any case, this is just an attempt at trying to understand. And do like, share, and comment if you like it, like the video. Definitely comment. Even if you don't like the video, just comment. Just comment. Say you suck. Stop doing this. Stop wasting bandwidth and our time. Stop wasting YouTube processing time, and stop wasting your own time. You can say all that. I won't mind. I'm not a physicist. See you tomorrow.